Hello everyone, and welcome to today's webinar, which is an introduction to computational fluid dynamics and a discussion of its role in enabling net zero. First, I will briefly discuss the CFD process and then the application of computational fluid dynamics in some projects related to clean fuels. So what is actually computational fluid dynamics? It is a powerful modeling tool which we use to predict the detailed three-dimensional behavior of liquid, gas, and particle flows. The three main stages of CFD are as follows. First, we need to define the geometry of interest. In this case, this is a Venturi flow meter. And then generate the mesh and discretize this geometry into cells. After that, we are ready to solve our simulation and post-process our results. The first step is the geometry preparation. We need to have a CAD of our geometry, and we can either create it using available 2D drawings, for example, general assembly or isometric drawings, or the 3D CAD file is provided to us. On the right-hand side, you can see two examples. The first one is the extracted fluid volume of a Venturi flow meter, and the quarter symmetry model is shown. At the bottom, we have the complicated geometry, which is a flare tip, and you can see the CAD here. After that, we can manipulate the CAD. It is very important that we make our geometry watertight. We shouldn't have any holes. And this is a process to clean up the CAD that might take a lot of time. And it's very demanding, but also extremely important to achieve. After that, it's good to do some simplifications of the geometrical features in order to reduce the cell count. Finally, we need to extract the fluid volume for our simulation in order to generate the mesh there. The fluid volume needs to be discretized into cells, which allow the solution of the governing equations of fluid flows, which are also discretized. At the bottom, you can see the example of the bunnies, where the resolution, when it is fine enough, we can see all the features and understand what the picture is about. However, when we represent it with fewer cells, this is not possible. So in a similar fashion, it's important to use a fine mesh to represent the geometry of interest, but also in order to capture accurately the physics. So the steps to create a good quality mesh are the following. First, we need to identify areas of interest for the flow and ensure that the minimum cell size can capture the important features. For example, on the right-hand side, you can see the mesh of a Francis turbine. It's important to capture the blades accurately, and therefore we need a cell size which is much smaller than the minimum dimension of these blades. After that, we need to refine the mesh in the critical areas and ensure that the aspect ratio and skewness are within acceptable limits. So in this case, we have a fine mesh especially focused on these blades. And finally, we need to ensure that the cell growth is acceptable and that it does not grow very sharply. And this is also, this can be observed in the pictures on the right, where we have the cell size growing steadily towards the outlet of the domain. Then we are ready to set up our simulation. We need to determine the physics and choose appropriate models. We need to question whether our flow is laminar or turbulent if we want to simulate heat transfer phenomena, and if we have a multi-phase or single-phase flow. Additionally, we need to consider if we want to take into account chemical reactions, combustion modeling, and so on. And another decision we have to make is whether we will approach our problem as a steady state or transient. On the right, you can see this triangle, which illustrates some different approaches of turbulence models. And as we go towards the bottom of this triangle, we are able to use it for problems of increased geometrical complexity. And this is achieved because we model more and more physics instead of actually resolving them. I should mention here, it's important to highlight that in the industry, we commonly use the RANS models, which stands for Reynolds average Navier-Stokes. Equations are solved here. And it's commonly used in the industry because models like the LES or DNS are very extremely expensive to use in actual geometries. Therefore, the RANS model are often preferred. The next step is to specify the boundary conditions. We need to place our inlets and outlets of our domain, select the walls and heat sources and heat sinks if there are any in our simulation. After, we need to define our fluid properties and solver settings and numerical schemes appropriate for our simulation in order to achieve convergence. Then it is time to start our simulation. First, we need to initialize the flow fields, and then we can run the simulation. However, we should monitor the solution convergence. So convergence in a steady state simulation means that the field variables are no longer changing as the simulation progresses and we have more iterations. And to monitor, we use the residuals, which are plotted on the bottom left graph. And also, it's a best practice to monitor the convergence of a property of interest. A variable of interest in this case is pressure. And I should mention here that the residuals quantify the error in the solution of the system of the equations. We want this error, of course, to be as small as possible. So in general, we aim the residuals to be below 10 to the power of minus 5. But in some complex geometries, this cannot be always achieved. So we might also accept the residuals in the order of 10 to the power of minus 3 and below, of course. Finally, we can post-process this converged, of course, solution results and extract information of interest. We can produce vector and contour plots and streamlines. On the right, you can see the ISO volumes of temperature from a flare combustion modeling. And at the bottom, the streamlines, which indicate the swirling flow out of these two bends, along with the cross vector velocity plot of a cross section. After summarizing the important stages of the CFD process, we can discuss some applications of computational fluid dynamics in projects related to clean fuels. TÜV National Engineering Laboratory recently built a facility for testing domestic gas meters with hydrogen. On the right, you can see the photo of our domestic gas rig. The gases are under high pressures, therefore relief vents are required. As the hydrogen is vented in the atmosphere, a major hazard is posed due to the fact that it is flammable and explosive even at low concentrations in the air. The hazardous area zones, therefore, need to be defined and we need to take appropriate measures. And these are the zones where explosive gas atmospheres may occur. In this study, zone sizes for the relief vents were calculated for the unlikely scenario that the pressure regulator fails fully open while it is venting hydrogen. The standard often indicates unrealistically large zones. However, it suggests that computational fluid dynamics can be used to calculate these zones accurately. Here you can see two photos of our facilities. And on the left, we have the high pressure relief vent on top of the cylinder cage. The natural gas building is at the back, hidden in this photo by the cylinder cage. And on the right, we have the pedestrian zone and the James Young building. The same building is pictured on the right from its other side, where the low pressure vent is on top of it. At this point, I would like to introduce an important term in our study. So the concentration of flammable gas in the air above which a fire or explosion can happen is called the lower explosive limit. And this limit for hydrogen is 4% by volume in the air. Therefore, we need to identify if the hydrogen concentration can be above this LEL limit in the pedestrian zones or in areas near electrical equipment. The shape and extent of the hazardous area zones depends on various factors. It depends on the wind speed and direction, the weather conditions, the geometry of the vent, the release rate of the gas, and also from its properties. And finally, it depends on the surrounding geometries, for example, the buildings and the trees. At this point, I would like to give a brief overview of the hydrogen dispersion study we performed. So first, we built a CAD model, including the main features, buildings, and boundaries. Then we created an appropriate computational mesh. We set up the simulation parameters and chose appropriate models. Afterwards, we ran a steady-state numerical simulation until convergence. And finally, we post-process the results in order to calculate the hazardous area classification zones. In this slide, the representation of the main buildings and vents with the CAD is shown. Here it's the front view, and if we focus on the top view, we can again see the natural gas building, the high pressure vent on top of the cylinder cage, the James Young building on the right with the low pressure vent on top. And we can see also where the pedestrian zones are located. So we started our hydrogen dispersion study with a high pressure vent, and NEL Clean Fuels team requested to consider worst case conditions for this, thinking that the wind direction is opposing the hydrogen venting direction. So they provided us all the necessary details in order to run this CFD simulation, such as temperature, flow rates, among others. Here you can see the computational domain for this study. And you can observe that the boundaries are placed far away from the area of interest. Here we are focusing on the area around the high pressure vent and close to the James Young building. So this happened, and we placed these boundaries far away so that they do not interfere with the flow. Additionally, you can observe that the cylinder cage here is not included in the model since it is mostly void, and including that would add a lot of computational cost in order to picture this geometry accurately, but actually doesn't contribute much to the flow. The same applies to the James Young building, of course, focusing at the end of it to the right. And this is the reason why we cut it almost in half, because this part of the building doesn't affect the flow in the area of interest. In this slide, you may observe a cross-section showing the computational mesh generated. So this mesh is a polyhex core mesh, a hybrid mesh which consists of polyhedral and hexahedral elements mostly. The mass refinement is required in the areas of interest. And here in this inset figure, we have the mass refinement zone around the high pressure vent and close to the James Young building in order to capture the hydrogen plume. We use mostly hexahedral elements in the bulk region, as in this region here, to reduce the total phase count. The polyhedral elements are used mainly to mesh the surfaces and also in the transition regions, as here, between different refinement zones. Polyprisms are used in the boundary layer. In our simulation, we consider the atmospheric air to have a composition 21% of oxygen by volume and 79% nitrogen. The mixing and transport of the chemical species is also modeled. Here, oxygen, nitrogen, and hydrogen. The fluids are compressible, and we employ the real gas model as an equation of state. Buoyancy is also considered since we took into account the fluid compressibility, but also gravity. I should highlight here that we used the steady state approach because we are interested in the steady state in condition of the plume, how far it reaches, and we were not interested in the evolution of the plume as the time passes. If that was our aim, we would have picked the transient approach. Here, some post-processing results are shown. On the left, we see the velocity contour plots and a cross section in the middle of the high pressure vent. And we can observe the flow separation at 2 points here as the air comes from the left and meets the building. Additionally, the streamlines are pictured on the right, which are the trajectories of the individual fluid particles that we use to visualize complex 3D flows as this one. So again, we observe, thanks to the streamlines, the flow separation, but also the recirculation zones, the eddies forming at the top of the James Young building on its first part. Here we have visualized again the streamlines colored by velocity, the velocity magnitude, where you observe that these recirculations, these eddies, have very low velocity. And at the bottom, we have also included the streamlines injected from the coming from the vent inlet. We can see that hydrogen initially keeps its original momentum and it's directed to the left, but it quickly turns to the right towards the James Young building and rises. Another way of visualizing our results is using the isosurfaces. These indicate the gas cloud boundary and define the volume where hydrogen concentration is greater than a specific value. For example, here you can see with green, colored with green, the isosurface, which encloses the volume where the hydrogen concentration is greater than 4%. Respectively, the isosurface, the blue isosurface, encloses the volume of air where hydrogen is above 2%. The concentration of hydrogen is above 2%. Again, we see that the plume is twisted and also directed towards the pedestrian zone, which is a bit alarming. However, if we see this picture at the bottom, we realize that it rises above all buildings. And at the ground level, the concentration is far below 2% by volume. And this happens because hydrogen is lighter than the ambient air, so the plume is positively buoyant and it mixes very quickly with the air. At this picture at the bottom, the spherical zone calculated using the standard is also illustrated. You can see that the results from CFD and the standards are pretty close considering the radius of this zone. However, the standard is very conservative, so we should have excluded and consider as dangerous all this, as potentially dangerous, all this zone. However, CFD tells us that at the ground level there is not a problem at all. And from this comparison, we already realize the benefits of simulating our problem using computational fluid dynamics. A similar process was followed to calculate the hazardous area zones for the low pressure vent. Again, the NEL Clean Fuels team wanted to consider the worst case scenario where the wind direction opposes the hydrogen venting direction. The post-processed CFD results indicate that we have a flow separation again as the wind is coming from the wind inlet from the left. And the streamlines show that they cannot follow the geometry of the James Young building, and they go around it and on top of it because it's not a streamlined body. In this slide, the streamlines are also colored based on their velocity magnitude. And we observe that we have low velocity eddies on top of the James Young building. And combining these streamlines coming from the wind inlet with the streamlines coming from the hydrogen vent, we can see them in the visualizations at the bottom of the slide. So hydrogen keeps its, because of its original momentum, the plume is then first directed to the left, but then it quickly rises because it's lighter than the air. After that, it has reached a certain altitude, then it meets the high velocity streamlines from the wind, and then it's pushed backwards. Again, we use the isosurfaces to visualize the concentrations of hydrogen that we are interested in. We can realize that the bend of the hydrogen is the plume of the hydrogen is bent backwards and directed towards the pedestrian zone. However, it has already started rising significantly. Looking at the comparison of our hydrogen plume with the one indicated by the standard, we can tell that it is highly conservative. It's overestimated. The size of the zone is overestimated. And if we've had used this indication from the standard, then we would need to exclude probably this pedestrian zone and redesign our facility. So we realized that also in this case, it was beneficial to use computational fluid dynamics to estimate the hazardous area zones. To conclude this study, CFD was employed to simulate the dispersion of hydrogen from relief vents in worst-case conditions. The hydrogen plumes were positively buoyant, and the gas concentration was well below 50% of the lower explosive limit at the zones we were interested in, the pedestrian zones and near electrical equipment, which can cause sparks, and it's a source of ignition, so potentially a fire or explosion. These results were then used to calculate the relevant hazardous area classification zones by the NEL Clean Fuels team for our new hydrogen facility for domestic gas meters. This was a very interesting study where CFD was used in the area of clean fuels for hydrogen. However, this is not the only one we have performed. Another example is a choke valve optimization study we did for Reenergize. So Reenergize contacted NEL to perform a choke valve optimization study using CFD. They have developed a hydropower system of energy storage and electricity generation that can operate even on low hills and small storage tanks. And this is thanks to a high density fluid that they use, which is non-Newtonian, and has a density 2.5 times the density of water. So this company aimed to reduce the pressure drop of choke valves they utilized in these hydro projects, where would they employ this high density fluid. So the objective of this optimization was to maximize the choke valve outlet pressure. To do so, the inlet and outlet diameters, as well as the cage opening area, were chosen as the design parameters. And this was done because based on previous sensitivity studies we performed, we found that these factors were most effective in performance improvement. A simplified CAD geometry is used for design space exploration in this study. And we generated 27 different geometries, considering the minimum and medium value and maximum value of these parameters, and therefore generated 27 different geometries and performing this amount of CFD simulations. You can see these geometries having the minimum and the maximum dimensions allowed in this picture on the right. At this point, I would like to discuss briefly the optimization process. So first, we performed the design space exploration, realizing these 27 CFD simulations, which were our sample points. After that, we constructed the surrogate model. You can see the surrogate model for one design parameter on the right, which uses the sample points, in this case, these CFD simulations, and in order to find the global minimum or maximum. Afterwards, we ran the optimization algorithm and validated the design. If the design was optimal, then we updated this. If the design was not optimal, we had to update the surrogate model. And if it was the optimal one, then our optimization loop was completed. The result of this optimization was a new geometry with a pressure drop reduced by 3%. On the right, you can see the pressure plots of this geometry, where we have also achieved a good pressure distribution in the downstream side of the cage. And additionally, looking at the velocity contour plots, we also have a fairly uniform velocity distribution in the downstream side. In this slide, we have the streamlines colored by the pressure and velocity. Apart from achieving a pressure drop reduction in the order of 3%, we need to point out that thanks to CFD, we simulated numerous different geometries computationally in order to find the global maximum. If we wanted to do this process in the facility, test these geometries experimentally, that would be very difficult to manufacture considering the big size of this choke valve. To give you some details, these choke valves have an inlet diameter of about 1 meter. So this would be an expensive process and it would take a long time. Additionally, this whole study was performed during the pandemic, so CFD is not affected by COVID in the sense that we don't have these limitations with and restrictions posed by traveling by COVID. The benefits are also visualized with CFD very easily, as you can see here, the improved pressure distribution and the velocity. To conclude, computational fluid dynamics is a powerful tool which offers significant insights on how complex systems perform. It can also be used to model cases where physical experiments are either expensive or not feasible. And we discuss in detail 2 examples where the experiments were quite expensive, or to be honest, not feasible in some cases. At the bottom, you can see some examples of recent CFD studies we performed. On the left, we have the CFD analysis of erosion of a cone flow meter, and then a flare gas combustion modeling simulation, and simulation of the flow through an orifice plate, visualized nicely here with the velocity streamlines. TÜV National Engineering Laboratory offers a suite of engineering tools to analyze flow phenomena such as single-phase and multi-phase flows. We also simulate particle flows, heat transfer, and we can model combustion and erosion as well, among others. Here we have 2 pictures on the right of our recent in-house high-performance computing facilities, our own cluster, which allows us to run simulations of complex geometries and complex flow phenomena very efficiently. At this point, I would like to thank you all for your time and attention, and I'm happy to answer any questions. Thank you.
Thanks for that, Lefke. Well, there's been quite a few questions posted, so let's jump right into the questions. How could you combine the CFD modelling with experimental testing at the NEL facility? And I suppose the extension to that question, Lefke, would be, why would you?
Thank you, John. So we very often combine CFD modeling with experimental data. We do so in order to tune our model and make it more accurate to represent the physical phenomena. To give you some example, we use very often our erosion facilities in order to do some coupon testing and fine-tune our erosion models. And using those, we can predict the erosion on flow meters and on different types of valves, and even get the deformed geometry using that data, and predict the drift in performance, for example. Another example is that we used our new hydrogen facility where some customers want to validate the performance of their flow meters. So we use the experimental data to tune our models, but they might want to test for operating conditions, for example, operating pressures that are outside the limitations of our facility. So we use this data, these fine-tuned CFD models, which are validated through experiment, to expand this data set, to extrapolate it. These are just a few examples where it's beneficial to combine CFD and experiments in our NEL facilities.
Excellent. Yeah, we've had quite a few questions on the hydrogen dispersion. So one of the questions here I have is how big are the hydrogen dispersion models, and how long did it take to run these simulations?
So these models were roughly they had roughly 80 million cells each, and these are considered medium-sized, let's say, models, thanks to the computational facilities available nowadays. So we used our HPC, our own cluster, to simulate those, and using about 150 cores. It took only a few hours to simulate those, and actually we got results within the same day. So this was very beneficial for us in order
Yeah.
to be able to do many relevant studies and tune and do sensitivity studies and see different parameters.
Okay, I've got two questions here left, Keith. Bear with me on this one because the two of them are linked. So one of them is was wind direction over the building considered, i.e., would the recirculation zone push the plume down or back towards the building? And the other one, which is linked to that, is on the hydrogen dispersion study, was any consideration made for a no crosswind condition? Wouldn't this be the worst case scenario, as there would be no wind to disperse the hydrogen, and so it would build up around the vent, potentially within the pedestrian zone? So,
So excuse me, John, could you repeat
yep.
the first part of the
Well, the
question?
first one, yeah, the first one is just talking about the wind direction over the building. Would recirculation zone push the plume back down towards the building? That's the first part of the question.
Okay, yeah, I see. So the recirculation zone, if you observe these streamlines, they had a very low velocity, so they couldn't push the plume downwards towards the building. Thankfully, they had low velocity, and also the momentum of hydrogen as it exits through the vent is quite high. So there, at this point, is strong enough. So that's why you see it very quickly rise and disperse. So simulation indicated that this is not the case, and it's not pushed downwards because of the low velocity regions there.
And what about the no crosswind scenario? Was that considered?
Um, I think that yes, that was considered. We simulated various few different um, flow conditions. We did a sensitivity study, and out of these, we saw that this was the worst case scenario that we should take into account in order to calculate the hazardous area zones.
Yeah.
And we were in a constant collaboration and discussion with the NEL Clean Fuels team about the conditions they think are more appropriate to look at.
Okay. Which turbulence models were used for the simulations and why?
So for both the hydrogen dispersion study and the choke valve optimization study, we employed the K omega SST model. This model is quite established in the community, in the industry, because it combines the benefit of the K epsilon model and the K omega model. So the K epsilon model is active in the free stream region or in the bulk region, while the K omega is active near the wall. And one other benefit of this model is that it can capture accurately the flow separation, which was an effect we observed in the hydrogen dispersion cases. And also it is quite accurate and relatively cheap, inexpensive. So that was another a factor that made us select this turbulence model.
Okay. What are the benefits of using the surrogate model for the choke valve optimization?
So the surrogate model is extremely low-cost model. It took only a couple of seconds to run. We performed these iterations about 100 times in order to make sure that we are not trapped in the local maximum in this case. So one aspect is that it's a low-cost model, and another thing is that it is not trapped in the local optimum, and as opposed to other gradient-based methods, which can get stuck in this local optimum and yes, this was the main reason why we chose this surrogate model.
Okay, good. Got a few people asking here about the software. What software do you use for your CFD workflow?
So we use ANSYS Fluent software. Most of the times we use the latest version, and we also use other ANSYS products for the pre-processing and post-processing stages of our simulation. So we use SpaceClaim to generate the geometries and manipulate them. And for the post-processing, very often we use CFD Post or Nsight, as well as ANSYS. Sorry, I forgot to mention that for the meshing, we most of the times use ANSYS Fluent as well.
Yeah. Okay. I'm just looking through the questions. I'm actually aware that some people have been posting questions on the chat function. I can't actually see those, so if you've got questions, if you could put them in the Q&A section, that would be helpful. Right, let's see. I've got one here. What was the time duration of the static CFD study for the first case study?
You mean for the hydrogen dispersion study?
Yeah, I'm assuming it was for the
So it is
hydrogen.
a steady state simulation. So we didn't use the transient approach. So we didn't simulate it for a few seconds, for example. So with the steady state, you can see the steady state situation, how far the plume goes, considering that you provide the hydrogen high pressure vent, the constant flow rate, the same flow rate.
Yeah, okay. One question here, was precipitation considered in the hydrogen dispersion model? It's rarely dry in East Kilbride, yeah. We should have allowed for snow as well then, I would have imagined.
No, it was not considered in this study.
It wasn't, okay. Right, on the hydrogen theme again.
As far as I'm aware, sorry about that, but yeah.
Okay. In the hydrogen study, if vortex shedding from localized buildings occurs, e.g. from the sharp edge corners shown, the result is a transient field, in which case how did you reduce data for changing ISO cloud mixture volumes? Well, that's a heavy one.
Yeah. So we did not.
That may be one you wanna get back to them on.
Yes,
Yeah,
preferably.
we'll
We
answer
did
that
not
one.
consider vortex shedding, but we can discuss that. We will
Okay.
get back to you with an email.
Okay, no, that's fine. Okay, I mean, I think we're there. As I say, I'm aware there might be questions on there that are not in the Q&A function. We will pick those up after this webinar, and we will get back to you. Okay, well, thanks again for joining us. I hope you found that useful. We covered a lot of ground there. Obviously, there was a lot of discussion around what we're doing in hydrogen. So obviously, if you've got any questions, please post them. We will get back to you. As I mentioned earlier, we will be sending you a copy of the presentation and the recording. Feel free to visit our website. I think we've got a slide for that somewhere left.
Yes, excuse me. Just to mention that these upcoming webinars,
Yep.
just this one, we have information about this one.
Okay. And yep, it's there, the website. So that saves me having to read all that out. So go onto our website, contact us on email if you've got any questions. And on behalf of myself and Lefgate, thanks for your time and enjoy the rest of your day.
Thank you all.